Hey, my name's Avery, and in this video we're going to be going over related rate problems and how to solve them. So we've just got one problem here, and it says a cylinder is shrinking in such a way that the radius is decreasing at 5 centimeters per second, and the height of the cylinder is decreasing at 2 centimeters per second, and we're wanting to find the rate that the volume of the cylinder is decreasing when the radius is 12 centimeters and the height is 10 centimeters. My first step when it comes to these problems is to highlight the different information that it's given us and highlight what we're trying to find. I think that just makes the solving process easier. So first, it tells us that the radius is decreasing at 5 centimeters per second. So I highlighted that. The height is decreasing at 2 centimeters per second, highlighted that, and then we're trying to find, like I said, the volume, the rate that it is decreasing when the radius is 12 and the height is 10. After I've highlighted everything, I just start to make notes of, again, the given information. So here, dr dt, that's the derivative of r, which is the radius, with respect to time. And that's going to be negative 5 centimeters since it says it's decreasing in the problem. Same thing with h. The height is decreasing at a rate of 2 centimeters. So your dh dt is going to be negative 2 centimeters per second. It tells you that when you're going to find the rate, the radius is 12 centimeters and the height is 10 centimeters. And then I also like to write out the formula, the original formula for whatever it is we're trying to find. So in this case, we're looking at the volume of a cylinder, and the formula for that is V equals pi r squared times h. And then here, this dv dt is the derivative of the volume with respect to time, aka the rate that the volume's decreasing, which is what we're trying to find. So that's why I put a question mark there. So the first step when you're approaching these problems is to try to decrease the amount of variables that's present in this volume or area or whatever it is that you're working with in that equation. But in this case, radius being 12, height and 10, they don't necessarily make a good ratio with each other to reduce with. So I'm just going to keep it as is. And your first step in finding dv dt is obviously take the derivative of the volume, which means you would also have to take the derivative of everything on the right side. So here you've got pi times, if you're looking at the derivative of r, that's going to be 2r, keep the h, so 2rh times dr dt, the derivative of the radius. And then same thing with h, you're just keeping that r squared, and the derivative of h would have a 1 coefficient before it. So the derivative would just be 1. Obviously, you don't write it, but you have to include that dh dt, which is derivative of height with respect to time. Next step, this is pretty self-explanatory. For trying to find dv dt, every place that you have a variable in this equation, you're going to want to plug in as much as you can what's already given to you. Luckily, this problem has given us all the information we need. We don't really need to do any additional solving. So I'm just going to start plugging in. You bring down your 2. Your r, like we said, equals 12 centimeters. And I didn't include units just so it doesn't crowd up the problem. We'll go back to those at the end. But your radius is 12, your height is 10, times dr dt, which we set up here was negative 5, plus your r squared, so 12 squared, times dh dt, which we set up here was negative 2. And if you move down, all those numbers simplified equals negative 1200 minus 288 times pi, which when it comes together equals negative 1488 pi. And the problem, as you see, says round to the nearest whole number, meaning you're just going to multiply this 1488 number by pi to get an integer value, and we round it up. So in this case, our dv dt, which is what we are trying to find, the rate that the volume is decreasing, is going to be negative 4,665 centimeters cubed per second. And one last thing, I know I said we would get back to units. This 12 would have a centimeters attached, this would have a centimeters attached, and then this rate would be centimeters per second. So centimeter times centimeter times centimeter is centimeter cubed over seconds. Same thing here. If you had 12 centimeters squared, that's 144 centimeters squared times your -2, which is centimeters per second, which once again would lead to that centimeters cubed. Also, it's a pretty just general rule when you're looking at things like volume for three-dimensional shapes, your final unit is going to be something that's cubed.